Okay, Unit 13, lesson number 8. It looks like we're finally getting around to doing spheres. Around? Yeah, okay, anyway. Okay, spheres. We want to look at surface areas and volumes of spheres. Of course, you can think of sphere, you can think of like a basketball, golf ball, baseball. Planet Earth is pretty close to being a sphere. It's actually an oblate spheroid because we're a little bulging at the equator, as the case may be, because of our rotation. But sure enough, if you want to think about a sphere, just think of some type of ball, and that's a pretty good approximation. For the mathematical definition, though, notice that the sphere is really like just the outer coating or outer shell. Right, so if you think about like a bowling ball, which is kind of like solid all the way through, or any kind of a thing like a baseball that's got some stuff inside. For math, when we're talking about the sphere, we're literally talking about just the points that are all the same distance from the center. Right? The point that is in the very middle of the sphere that we're all equidistant from, we call that the center. And of course, we've got a radius. Right? Anytime we play with the circles, we got to go with our radius, and our good old friendly number pi is going to show up. And so the distance from the center of the circle to any point on the circle is the radius. Now, we can also have a chord, and kind of similar to a circle, where a chord went from part of the circle to another part of the circle. The chord will go from a part of the sphere to a different part of the sphere. So the endpoints have to be on the sphere. So if you can imagine just walking right outside and taking a shovel and digging down in the ground and keep digging until you come out someplace else on the earth, that would be a chord. If you're ever curious about where you would come out if you dug straight down, figure out what your latitude and longitude is, and then figure out the corresponding place on the other side of the planet. And if we're to actually dig straight down from Seattle, Washington, we would actually come up somewhere in the Indian Ocean. So, very wet conclusion to our hypothetical journey. And of course, just like a circle would have a diameter, our sphere will have a diameter. So just like on a circle, we said, hey, if the chord goes through the center of the circle, we call it a diameter. Same thing with a sphere. If the chord goes through the center of the sphere, it's a diameter. And yes, just like a circle, the diameter is twice the radius. And those are distances. Right? So if you're talking about the radius, you might be feet or inches or miles or centimeters. When we get into surface area, again, it'll be like square feet, square inches, square miles, square centimeters. And when we talk about volume, it'll be cubic units, right? Cubic inches, cubic miles, etc., so forth and so on. Let's continue with our journey. Now, if you're trying to figure out how a plane could intersect a sphere and have only one single point of intersection, well, imagine putting a basketball on the ground, right? In a perfect mathematical setting, that basketball would be a sphere, the ground would be a plane, and it would touch at just exactly one point. And then, of course, other times, the plane would slice through the sphere, creating a circle. If that plane happens to include the center of the sphere, it's not any old circle, it's a great circle. Think about the equator on the planet Earth, and you got a pretty good idea of what a great circle would be. or any line of longitude. If you followed around the globe, that would also create a great circle. Plane routes are usually great circles. If you're going to fly from, say, Seattle to London, you would fly in a great circle path around the globe. Now, unlike planet Earth in math, a sphere is actually a perfect sphere. Right? Planet Earth is not a perfect sphere. It's a little bit bulging at the equator. But the circumference of a great circle is the circumference of the sphere, and all the great circles would be congruent to each other. And of course, a great circle cuts that sphere right in half, and we call those halves hemispheres. Of course, sometimes with geography, we talk about the northern hemisphere and the southern hemisphere of our planet, whether you're north or south of the equator, or sometimes we talk about eastern hemisphere and western hemisphere. That's a little bit more arbitrary because we talk about the international date line, but it does cut the planet into two hemispheres. Now, notice when we were working with a sphere, the only number we're going to play with is the radius. Right? We're not going to talk about height or width or length. Right? The radius is going to be the star of the show. So if I know the radius, I can figure out the surface area. 4 pi r squared. Similarly, with volume, the only dimension I need to know is the radius. If I know the radius, I can find the volume. 4/3 pi r cubed. Notice in each case there is a 4. In each case there's a pi. In each case there's an r. And on volume, you see the radius to the 3rd power, and then there's dividing by 3. When you get to calculus, you're going to find out how those 3's cancel each other out to leave you with the radius squared, which is the surface area. But that's a couple years down the road. So surface area, 4 pi r squared. Volume, 4/3 pi r cubed. So let's do a couple examples here. Well, I know the radius is 8. For surface area, it'll be 4 pi r squared. Of course, 8 times 8 is 64. 4 times 64 is 256. So I've got an exact answer, 256 pi square inches. If I want to use a calculator, I can multiply 804.25 square inches. Okay, let's get the... Of course, let's take a look here at the volume. Ooh, this is a little tricky. We don't know the radius. So if I look and the diameter is 40, I can figure out pretty quick the radius must be 20. So 20 times 20 times 20, 8,000. 8,000 times 4 is 32,000. 32,000 is not divisible by 3. So there is an exact answer. 32,000 thirds pi cubic feet. Or if I grab a calculator. Now, notice when the answer starts getting this large, we're talking about 33,510. I'm not going into the decimals here. I just rounded off to the nearest whole number. instead of like the nearest tenth or the nearest hundredth. Because I'm like, oh, come on, we're up to 33,000 at this point. Ooh, this is fun. We can find both the surface area and the volume of this sphere. And the radius is, I don't know the radius. And unlike the previous example, it's not maybe almost quite so easy to eyeball it. So I got to put on my thinking cap and say, okay, I know the circumference of any circle is 2 times pi times r. And for this sphere, that great circle has a circumference of 6 pi. So let's figure out that radius. Divide each side by 2 pi. The radius is 3. Now I can go about finding the surface area. 3 squared is 9. 9 times 4 is 36. 36 pi square feet if I want an exact answer. About 113.10 square feet if I want a decimal approximation. Volume, 4/3 pi r cubed. 3 times 3 times 3 will get me a 27. Hey, 27 divided by 3 is 9. No, I still have to deal with that times 4. 9 times 4 is 36. Hokey smokes, Bullwinkle, how about that? 36 pi cubic feet instead of 36 pi square feet. And then for the volume, 113.10 cubic feet, as opposed to the surface area, which is 113.10 square feet. Really cool how that worked out when the radius was exactly 3. Hey, I got a string quartet of cats. Oh, no, I guess it's not a quartet. We have I guess it's the whole band showing up. The string band. So we got a worksheet. And then the IXL ties in quite nicely. The IXL will deal with the surface area and volume of spheres.